Welcome back to P3. Today we're looking at functions and mappings, Unit 2.2 in your International A-level books. Now a mapping just transforms one set of numbers into a different set of numbers. The mapping could be described as words or as an algebraic equation. And often this kind of thing can also be represented by a graph. Now, what's quite important here is when we start looking at functions. So mapping, just kind of has an input and a very distinctive output. So it's just very much the same as what we're looking at in terms of functions, which is the important bit here. So a function can be 1-to-1 or it can be many-to-one. Okay, and that's the important definition of a function. So an example of a 1-to-1 function could be, say, like a linear graph, 3x plus 5. And when I look at that, every value of x will have a distinct value of y, my f of x. Yeah, so I substitute an x value in, I get a distinct value for my f of x for my y. Okay, as this could also be y equals 3x plus 5. These are essentially the same things, aren't they? Okay, so 1-to-1 function. In terms of graph, we're essentially looking at something like a straight line graph. Now, many-to-one is when we look at, say, something like an x squared graph. So like this. So this is many-to-one. So this one is 1-to-1. And now we're looking at many-to-one. Now, why is this many-to-one? Well, if I think about how this graph looks, something like that. And if I think about, say, values of x, so if I think about a value of x, say -1, it gives me a very specific value of y, doesn't it? -1 squared is 1, -5 is -4 there. But also, 1 will give me that same value of y. So there are multiple x values and they give me a singular y value. Okay, so this means that there are many inputs that give me that single output. Okay, so many-to-one, that's what we're thinking of. Now, those are the two that are a function. Now, if I think of something slightly different, like a y equals square root of x, or an f of x equals square root of x, either way I write it. Now, how does that look? This one's going to look something like this. Okay, excuse my drawing, obviously not perfect there. Now, if I pick a value for this one, it's a little bit different. So I pick, I don't know, x equals 9. I can get a value that is +3, I can get a value that is -3. Okay, so this has a single input, but it has two outputs. Okay, and this means this is not a function. Okay, so let's just recap quickly. 1-to-1, whereas one input, one output, is a function. Many-to-one, where there's more than one input but a single output, is a function. When I look at the reverse of that, 1-to-many is not a function. However, we can turn it into a function if we limit values. Then what we can do then is turn something that's not a function sometimes into a function. So again, if I took this y equals root x and limited my value. Now it's pretty obvious that we need to restrict our x values. Now our x values, our input is called the domain. Okay, so it's very important that we restrict our domain. So when we're looking at writing this, we're going to be, for example, y equals square root of x, where x is an element of our real values, and then we want to let everyone know x has to be greater than or equal to 0. It's kind of a given. You know that you can't do the square root of a negative number. Obviously I'm excluding imaginary numbers in that statement, but for real numbers you cannot do the square root of it. However, just as it stands here, which is kind of how it's written in the book, this is still technically not a function, because my diagram here in red also is exactly the same as this. X is greater than or equal to 0, but it's still not a function because it is one to many. So I need an additional bit, and it means that I'm also limiting my y value. So I'm limiting it. I want just the positive one. So this is called the range. So the range is my outputs. So in most of these cases it's the y value. And therefore then this square root of x can become a function. And we can do this with quite a few non-functions to turn them into functions, just by limiting either the domain or the range. Usually we do focus on the domain. So let's have a little look further. If I have a function f of x equals x squared, and I'm going to set my domain, so my inputs, my x values, and I'm going to set that to x being a real number, an element of the real numbers, and I want it between 5 and minus 5, sorry, so minus 5 and 5. So I'm setting a specific domain here. So when I think about that, I know what my x squared graph looks like. It's going to look something like this. Okay, now if I think, right, well, this is the point at minus 5 and plus 5. So what I'm doing there means I'm actually getting rid of that top part of my graph. I'm only doing it between 5 and minus 5. And if I think across to then where these hit the axes, I know that 5 squared or minus 5 squared is 25. So that's 25, I know this is 0. So first things first, I know f of x is a function as it's many to 1, and I know that it has a range of between 0 and 25, and I'm just going to do that with an inequality like so. And that's just talking about the graph, so it's just the domain is those x values, the range is those y values. And that's the general thing what you need to be thinking about when you're doing this. Now, a function, say my f of x, this could be written in a different form. So I could be writing it like something like this. And what that's basically saying is that this function is actually kind of made up of almost two functions, where something happens when it's less than 1, and a different thing happens when it's greater than or equal to 1. So if I want to do this, I need to start thinking, right, how do each part of my graph go? And then start looking if I want to find the range and so on. So let's have a little look at that. Now, key values or critical values here would be when x equals 1. So if I'm looking at this top one, 5 minus 2x, and I'm going to look at what happens when x is 1. So 5 minus 2, so that's 3. It's a critical value. The graph doesn't actually touch that point because it's not equal to 1 there, but it is important. It's a critical value in our diagram. Let's look at the other part of the graph. So x squared plus 3. So an f of 1 here, that's 1 squared plus 3, and that's 4. Again, it's another critical value. So when I come to draw my graph, I need to take these points into consideration along with how the rest of my graph looks. So the first part, 5 minus 2x, means I'm going to cross at 5. It's a negative 2x graph, and then it's basically going to stop at this point where x is 1. And I'm just going to put a little circle there just to show that it's hitting that point almost, but it doesn't include that point. Now when I look at the second part of my graph, where I'm also looking at 1, but now I'm looking at what happens after 1. So this part is what's happening at x equals 1 and before it. Now I want to look at what's happening at x equals 1 and after it. So that's this part of the graph, x squared plus 3. So we know what the shape of an x squared graph looks like. And at 1, we're actually at 4. So we're just in between there. And the shape of this graph is something like that, increasing. And there is a very quick sketch of my diagram, of my function. Now, when I'm looking at, say, what's my range? Well, in this graph, my range is the set of y values that this will take. So it's from here up. Now, if you remember, let's do this one in blue. If you remember that this point is at y equals 3 there. It doesn't actually hit that point, but everything above that point counts. Everything above. Going off that way and off this way. These are going to go on forever, aren't they? So everything above that point counts. So for my range, I'm looking at greater than 3. Not equal to, but just greater than. And then finally, I could be given a question like solve this, f of x equals 19. So this is going to happen, somewhere up here. F of x equals 90 is going to hit both my graphs, one in the negative side, one in the positive side. So doing this, I just need to then essentially set up two equations because I know it's going to hit both of these graphs, or both parts of my function, if you will. So here, nice and easy, so take my 2x over this side, negative 14x equals negative 7, and then look at this one, x squared equals 16, x equals plus or minus 4 technically, but in this case it has to be just that positive 4. That's the only part that actually works with my function. If you remember this part of the function, it can be, the x can only take a value of greater than or equal to 1. And that's it done. So here are a few for you to try. Pause the video as you need to. Okay then, so let's have a look at some answers. So this one is many to 1. You can pick many x values and they will give you that same y value. And yes, it is a function. Let's look at b. Well, b is 1, 2, 1. We know that. However, this is not a function. So something I think I might have missed out at the beginning. The reason this one's not a function is because we don't have anything valid at the asymptote. So for it to be a function, every value on the domain must map to a value on the range. Okay, so every x value must have a y value. And in this particular case, wherever this asymptote is, so say it was at x equals 2, that value 2 doesn't have a y value, it doesn't have a value for its range. Okay, and because of that, it cannot be a function. Okay, so this one, if I think of a value of x, it gives me two possible values of y. So this is one too many, so not a function. And then finally, if I look at this one, we've got x gives me a y. You can see it's actually 2x will give me that same y. So this is again many to 1. So it is a function. Okay, so part A, well, the explanation I'm just going to give you to verbally, but this is what I'm looking at here. Okay, in the g of x, if I look at x equals 4, so at x equals 4, there is no y for my g of x. So what I'm kind of looking at here, and I would obviously explain that a little bit better, but essentially what I'm doing is that there is no valid value for y when x equals 4. So on the domain when x is 4, there's no y because it doesn't exist. X equals 4 doesn't exist. You know, so I've got x is less than 4 and x is greater than 4. Although I'm not sure if this is a particularly great question, if I'm totally honest with you. Question part B, sketch the function f of x. So quite a quick one. Again, we're looking at our values. Our critical values will be at 4. So when x is 4, what's happening? So when x is 4, we are hitting that point, which I'm going to do here. So say this is 4. So 4 minus x is going to be a negative graph. It's going to look something like this. Obviously hitting here on the y-axis at 4 as well. What's happening after that? So as x is greater than or equal to 4, we've got the x squared plus 9 graph. So look at what happens. So when x is 4, you get 16 plus 9, which is 25. So I can't really fit it in, but I'm just going to put it here. So you're just going to have to imagine. I don't know if I can move this one. No, typical. So you just have to imagine it's a curve up here somewhere. Okay, sorry, I couldn't deal with the graph, so I've just moved it down and sorted out a little bit. And just one more thing that I didn't notice when I've rewritten the question down here, this one should be a plus, as it was in the question. Part C gets quite easy from here. F equals f of 3. So that's going to be in the first part of the graph. So it's 4 minus 3. So that's going to be 1. Looking at D, and F is 10. That's in the second part of the graph, where x is greater than or equal to 4. So it's 10 squared plus 9. So it's 109. solve when f a equals 90. So this is going to happen in both parts of the graph. So we've got two possible solutions to this one. Just make a little room there. So let's do it, start it up here. So f of a now equals 90. That's what we're looking at. So we've got 4 minus x. Sorry, the x will actually become an a, won't it? And that equals to 90. So a is going to be equal to negative 86. That's one solution. And x squared plus 9 equals 90. And again, I do apologise that x squared will become a squared when I substitute the an, because it's f of a. A squared equals 81, a will equal 9. Okay, and it must be a positive 9 there because of the limits in my question. And finally, question 3. So we need to start with a sketch, which I think I would have started with even if we weren't asked to do a sketch. So we've got from minus 10, 14. So let's go like minus 10 across, 14 up. Let's put it about that. So this is my minus 10, 14, and I'm going from up to minus 4, 2. Let's put that about there. It's linear, joining those up. So that's at 2. Sorry. That one's at negative 4. This one's at 2 there. And then we go from that point, minus 4, 2, up to 6, 27. So something like this. Okay, and that is essentially the sketch on my graph. Okay, I can just put the values on the axes, or I can put the values as I've just done on a couple of these coordinates. It doesn't really matter. I think it's better if you just put it on the axes, but you know, just for clarity, I'll leave it as I did with a little bit extra information. State the range. So if I'm looking at the range of g of x, the largest possible value there is 27, and I can get that actual value, and the smallest possible value there is 2. So my range is greater than or equal to 2, less than or equal to 27. Now for part C, where f of a equals 12, if I think on the graph, 12 is just under this 14. So there's going to be a value this side and a value this side. So I'm going to get two values out of this. So let's have a little look. So I really need to know what the functions are for this. So I need to work them out. So I want to look at the gradient. So let's look at the one that is essentially between the minus 4 and the 6 on from the domain. So difference in y's over the difference in x's. This is one way of doing it. So we got 27 minus 2 over 6 minus 4. So it's 25 over 10. So divide them both by 5. So 5 over 2 is my gradient. So y minus y1 equals mx minus x1. So y minus, let's do the 2 and the minus 4. 5 over 2 x minus 4. So I'm just going to skip a few steps here, but we get 5 over 2x. 5 over 2 times a positive 4 is positive 10. Plus 2, so that's going to give me 12. So that's my first function. Just going to go onto a separate page. And before I do, I should put that x in there. Also, just while I'm looking, I do this sometimes. just written f of x when it should clearly be g of x. Don't know why I do that sometimes. I think it's just force of habit. So g of a equals 12. That's what we're looking at. So that equals the 5 over 2x plus 12. Take away 12, so we get 0 equals 5 over 2x. So x must equal 0. So that's one solution, and I do apologise. It shouldn't be x. We need to be consistent. It should be a. Easy to do. I know a lot of people do the same kind of mistakes, revert back to x. So here's my coordinates for the second part of the graph, and for this one I'm just going to use a slightly different method just to give you more options. So rather than work out the gradient first and then calculate the equation of that line, I'm just going to do it in one go. So y minus y1 over y2 minus y1 equals x minus x1 over x2 minus x1. Okay, it doesn't matter which one's 1, which one's 2. So let's do it this way. So y minus 14 over 2 minus 14 equals x minus 10 over minus 4 minus 10. So we got y minus 14 over minus 12, x plus 10 over 6, and then let's multiply by the minus 12, x plus 10 over 6, we'll cancel in there. Y minus 14 equals minus 2x minus 20, y equals minus 2x minus 6. So that's just another method. I mean, I personally prefer to just find the gradient first and then use y minus y1 equals m x minus x1. My personal preference, but for those of you who want another way, here is another way. So we're looking at g of a equals 12, so minus 2a minus 6 equals 12. So we've got now 2a equals minus 18, a equals minus 9. So my two answers to this were a equals 0 and a equals negative 9. And that's it done. If you liked the video, found it useful, please like and subscribe, and I will be bringing more videos each day for all the units in International A level.